Okay, let us start our second morning talk. Evgeny Smirnov from Independent University of Moscow and Guangdong Technion. Yeah, and his topic is closely related to what Toля Kirillov doing now, like
Yeah.
Lascoux polynomials and Gelfand-Zetlin polytopes.
So yeah, thank you, and it's really a great pleasure for me to be here. It's my first time here in Bimsa, and thanks to Ivan and to Evgeny, and of course thanks to Tolia for bringing all of us here together. So yeah, and I'm going to speak about Lascoux polynomials and Gelfand-Zetlin polytopes and Gelfand-Zetlin patterns, and we already saw a photo of late Alain Lascoux with Tola, and so let me now define the Lascoux polynomials and well, what my main topic of my talk will be some new perspective on of viewing Lascoux polynomials as certain, I would say, weighted Euler characteristics of certain subdivisions of Gelfand-Zetlin polytopes. Okay, so let me first introduce our main characters, who are Lascoux polynomials. This is a superfamily of several important families of polynomials in algebraic combinatorics, such as Schur polynomials, key polynomials, and stable Grothendieck polynomials. So I will take. I will start with taking the symmetric group Sn. Everything will be in type A today. So and Sn is generated as usual by n minus one simple reflections. And let me take W naught, which is the longest element in Sn. So it has, well, several presentations, many of them. And for instance, you can present it as, let's say, S1 times S2 S1 times S3 S2 S1 and so on, Sn minus 1 S2 S1. Okay, so the length of this guy is n choose 2. So and let me define the divided difference operators and um, I and other operators I'll call phi I, depending upon beta happens certain parameter, and these will be operators on ring of polynomials. Well, in fact, you can say there in many variables here, or n of them, doesn't matter. I prefer to put integer coefficients. And what is the divided difference operator? This is the following thing. So having f x1 as n, some polynomial in n variables, what you can do is you can flip two variables to neighboring variables, x1 and 2, or xi and xi plus 1. So this will be called si of f with two variables flipped. And now you take f and subtract it. So this thing is skew-symmetric in I and I plus 1. So as the first course in algebra teaches us, it is divisible by xi minus xi plus 1. So this is a polynomial. Right? So this thing vanishes at I equals to xi plus 1. So this is a polynomial again. And this is a divided difference operator. And if you take a homogeneous polynomial, the degree either drops by 1 or this thing is 0. So 0 if it is symmetric in plus 1. And then what else we can do? I want to get an operator that preserves the degree. So this, I think this was done by Si, Si of f xi plus 1 is just changes the variables xi plus 1. Yeah, so these operators, they satisfy the same relations as elements in the symmetric group, except for idempotency. So the square of such a thing is 0, but they still satisfy braid relations and commutativity, so they form something called Nilf-Hecke algebra. And so if you want to know more about this, ask Tolle. He's great expert in this. So and what I want to do now is I want to introduce some cousins of these operators. These will be called phi I with some parameter beta. Beta is just a formal variable. So of f, this will be you need to take the following thing. You take xi times f plus beta times xi plus 1 times f, and you apply the divided difference operator to this guy. So that's what you get, and you see that the well, if you apply pi to f at beta equal to 0, so if there were no part here, this would preserve the degree. But if you add beta, then, well, you get a term of degree larger by 1. But if you want this thing to be homogeneous, you can say that if the degree of beta is -1, the phi I beta is homogeneous. Okay, so now let me, let's do a quick example, which will be kind of key example for us. That what happens if you take x x1 to the power k, and what happens if you apply p1 f, p1 of beta. This means that you need to apply 1 to x1 power k x1 plus d1 beta x1 to the power k x1 x2, something like this, right? So this is just sum of geometric progression of the following type. This is x1 to the power k plus x1 to the power k minus 1, x2 plus etc. up to x2 to the power k, right? And this has one term less, but they all start with beta plus beta x1 to the power k x2 plus beta, well, beta here, x1 k minus 1 x2 squared plus, and so on and so forth, x1 x2 to the power k. And let me write this as a picture, as the following picture. I'll write x as dots, so this will be x1 power k, will be x1 to the power k minus 1 x2 x1 x2 squared up to x to the power k. So I kind of decrease, I kind of I don't know, push string of beads out of x1, and these guys, so beads are my x's, and these guys here are parts of the string between the beads. So this is beta x1 ax2, beta x1 a minus 2 x2 squared, and so on. So this will be key example. So just let's keep it in mind, and we'll see that we will kind of generalize this example. So you see that zero-dimensional points correspond to x's without any beta, and one-dimensional correspond to something with beta to the power 1. Okay, so who are now Lascoux polynomials and their friends? Uh, so suppose you take an element of Sn and you take some word representing this element. So let W in be an element of Sn, and it's I1 as I2, etc. as IL. Let this be a reduced decomposition of this L of W L. So this is a reduced decomposition. Okay, and then let me take some lambda, a partition of n. Right? So lambda is sequence of integers, lambda 1, lambda 2, lambda n, weakly decreasing. Right? So a Young diagram, or highest weight of a representation of GLN. Okay, and yeah, this will be important for us. And and now what am I going to do? Well, so x to the power lambda will be x1 lambda 1, etc. xn to the lambda n. Such a usual shorthand notation. And let me now take this decomposition and apply these letters, apply the pi's corresponding to these letters to x to the power lambda. So basically what we did in this case. So this is the simplest example for S2, right? So, well, and one component partition. So if you add x2 to some power here, there will be just some other degree of x1, x2. Okay, so anyway, definition. Lascoux polynomial L lambda and W is defined as follows. We take pi's I 1 beta I L beta applied to x to the power lambda. Yeah, yeah. Okay, thank you for this comment. I didn't know that Lascaux was rejecting this. So yeah, this indeed this goes back to your paper with Sergei Fomin in 1994, I guess. Exactly. Yeah, of course. So, well, these are just Demazure operators. And, I'm going to speak about them as well. And yeah, this is connective K theory. That's right. And I was going to mention this in maybe 1 minute. Okay, Lascoux. You know Arnold's principle, right? So Lascoux polynomial. Let's say Sergei Fomin, Anatol Kirillov, 94, right? Not that. 6 maybe. I don't know. Okay. So yeah, and okay, so mm, yes, well, indeed, in many cases, people just consider beta equal to -1, and they get a nice polynomial with changing signs, which and let me now present the following picture. So, if you take this Lascoux polynomial defined by Kirillov, and you specialize it at, well, you can specialize it at beta equal to -1 as Lascoux proposed, or you can specialize it at 0. So in this case, you'll get just a Demazure operator. And what is so this? There is one direction specializing it at beta -1. Well, let's put beta. Beta. Or you can just specialize it. Well, you can consider it for W equal to W naught. In a sense, it's the most interesting case. This thing will be symmetric, and it has a special name. It's called stable Grothendieck polynomials because of Grothendieck polynomials, which were produced, well, of course, not by Grothendieck, but also in this paper, right? Or like analogs of Schubert polynomials, K-theoretic analogs. And this is G lambda. Uh, Schubert or Schur, this is Schur is the particular case of Schubert, and I'll go to that. Yeah, these are extension or one parametric extension of Schur polynomials, and that's what you get if you specialize it at beta equal to 1 as lambda Schur polynomial. These are stable Grothendieck. And here you get, here you get some, if you specialize this at beta equal to 0, so if you take only like this part, this in this case you get something called key polynomials, depending also on two parameters, lambda w. Well, they depend upon a partition, and for w equal to w naught, you get Schur polynomials. So these are superfamilies of 1, 2, 3 families of polynomials, as with the name here, key polynomials. And let me tell you a few words um, about these guys. Where do they appear? They appear as characters of Demazure modules. So if you take, let's say, if you take representation B lambda GL n module, well, you can just draw weight polytope, and there you have the highest weight lambda and the highest weight vector, say, and then you can act by the while group and get these elements, like extreme vectors. And suppose you take an extreme vector. Well, if you act on this guy by the Borel, you get nothing, right? So stabilized by the Borel, it's what the highest weight vector is. And for instance, if you take this one, you get, well, you'll be able to get this part, something like that. Okay? And what you get if you take the linear span of it, linear span of a Schubert variety, if you prefer geometric language. So if you take inside V lambda, you can take B applied to W times V lambda plus, and then you take its linear span, and this guy is called Demazure module, which is a B module, not G module. So this is a B module. Of course, it's G module only. This is highest or lowest weight. In the case of lowest weight, it's the whole thing, right? So, and it's exactly the case where you get the character. Well, so key polynomials are characters of these fellows. So key polynomials, k lambda, kappa lambda, w are characters of Demazure modules. And in particular, well, as everyone knows, maybe from the kindergarten, that Schur polynomials are characters v lambdas, right? And yeah, that's right. That's why I apply this w to v lambda. Yeah, this is extremal vector. Hmm. Yeah, that's in fact that's what I write here. Maybe it's not the best notation, but yeah, the thing is that you're acting by your w on partition, and you get a composition. Well, if yeah, that's right. Or otherwise, I can say that they are defined for a partition and a permutation. Okay, that's how I prefer to do that. So if you don't mind, okay. Mm, And well, these guys upstairs, they correspond to connective K. Well, these guys correspond to connective K theory of Schubert varieties. Well, elements of Riemannians. So um, these guys. Hmm, well, I don't want to go to geometry. This would lead us too far, but I'll reference to Anders' book here. We studied this combinatorics a lot, and there is there are a series of recent papers on these on beta Lascoux polynomials by well several people. You on and yeah. So this is a very active subject, and as far as I know, these guys don't have geometric or representation theoretic meaning. They're just can be defined combinatorially, and what are they actually good for? Well, I think this is yet to be discovered. So, but I will I will go now to I will pass to our results on key polynomials, and then on its generalization to Lascoux. Okay, so for this, let me um, define Gelfand-Zetlin polytopes. Second main character of my game. And oh, so that's mission. All right. So so we start with a sequence lambda, let me now order these lambdas right to left in weekly decreasing order, weekly increasing order, and let me now introduce what we call the Gelfand-Zetlin pattern. This will be a triangular tableau of numbers. This will be 1. This one will be x1, 1, x1, 2, x1 n minus 1, x2, 1, x2, x2, n 2. Like every row is shifted by 1/2 with respect to the previous one. Here you get x n minus 1, 1. And given this table, given x, y, z, you apply, you view this triangle and each triangle in this tableau as two inequalities. X, y is between x, okay, and these guys are fixed. So these guys, x's, are variables, and they give you a bunch of inequalities. So and they obviously define some, well, convex bounded body, also known as polytope. So this is Gelfand-Zetlin polytope corresponding to lambda inside R power n choose 2. And if lambda i's are all distinct, this is full dimension. Lambda I not equal to lambda j, just full dimension. And then, well, let me draw the simplest example, and the only example I can draw for a, b, c, x, y, z. This polynomial will look as follows. Something like this. So you see it's like combinatorial cube with one edge collapsed. So it is non-simple. Here you have a non-simple vertex. And, well, that's how it is. Okay, so, and also you can define Gelfand-Zetlin patterns in GZ pattern. By definition, this is an integer point, my Gelfand-Zetlin polytope, so a collection of x's, integer. So x, I, j, r, c. So as well, Gelfand-Zetlin introduced them in 1950 to index certain bases in V lambda. So Zetlin, yeah. That's I don't, because, well, they are just shift. Well, you can shift it to be positive. Well, whatever. So yeah, you can just shift all x's and lambdas by any number. Well, first add 100 to them and make them all positive. Okay, so so these patterns, using patterns, index bases in lambda, some very nice bases, and okay, let me make them non. Okay, right. So and let me yeah, let me take, and, well, bases of weight vectors and vectors of the following weight. So pattern xij corresponds to basis element weight get this weight, you need to sum up the pattern by rows. So this x1, x1 n minus 1, x2 1, etc. plus x n minus 2, x n minus 1. So this is the weight. So if you sum up over all points, something like the exponential of this thing, or just put formal variables into these powers, what you get will be exactly polynomial as this thing tells us. So this was generalized to key polynomials, and this generalization is not. Oh well, yeah. Of course, the uh-huh. Uh-huh. Okay. Yeah. Yeah. Sorry. Yeah. Okay. So, okay. And what we did with Valentina Kiritchenko and Vladimir Timorin, uh, uh, our goal was to define to get a description of key polynomials. So we described a way to get to assign to each permutation a collection of faces of Gelfand-Zetlin, some special collection of faces of GC polytope. Well, this actually this collection was such a collection, such a relation was also appeared in slightly different way in papers by Misha Hogan and Ezra Miller. But uh, what we do, we assign to each permutation a collection of faces in such a way that if you take all integer points, well, um, some permutation, you assign the back face there, or assign like these two, this and this, and you see that, well, this blue guy actually looks like this orange guy, like a character, like a trapezoid. It's not a coincidence, because if you project it in this way to r n minus 1, and if you sum up by all integer points in our collection of faces, well, let me call it gamma w, and collection of faces. So theorem is that the key polynomial lambda w corresponds to some x to the power p, let's say p, a Gelfand-Zetlin pattern with with a corresponding point in this collection of faces. Well, I have not enough time to describe how this collection of faces is, but it's some combinatorial procedure. Pattern, let's say, inside gamma w. Okay, so we basically, for w equals w naught, we recover true polynomials as in the classical case. Okay, so this was right, and now question is, can we like pull out the Lascoux polynomial from here? And the answer is yes. That in fact we can do the following. Well, these are just sums over integer points, and this is something sum over, well, not just integer points, but also like intervals, spaces of larger dimension. So we know, well, there exists, as we showed, there exists a cellular decomposition of GZ lambda. So there, we constructed some cellular decomposition of, well, C decomposition of GZ lambda. Um, and the zero um, zero dimensional cells are exactly the integer points, the set of GZ lambda sected with z to the power n choose 2. And kind of, you need to subdivide it into some pieces, chop this polytope into pieces. Most of them are just cubes, just unit cubes, but some of them are not. Like interesting things happen on the boundary. I'll show you a picture in a couple of minutes. So, and then to mm, to a face of this composition, you assign a monomial. Well, and this there's also combinatorial language for describing these cells by something called enhanced Gelfand-Zetlin patterns. You just add some bells and whistles with some edges and marks on vertices, something called enhanced GZ patterns. And a pattern, well, let's say enhanced pattern P, also corresponds to a polynomial in x's, x1 to the power something, 1 and to the power dn times beta, beta to the power r, where r is exactly the dimension of this cell. R, dimension, well, rank of pattern, dimension of the corresponding cell. Okay, and then, well, let me, uh, yeah, but this correspondence, sometimes you get 0. Sometimes some bad cells correspond to 0. X to the power p corresponds to 0. Well, in this case, we call an enhanced pattern inefficient. But the theorem by Presnova and myself is that the Lascoux polynomials, lambda w, are obtained as the sum of x to the power p over all enhanced pattern in gamma w in this collection of faces defined in this theorem defined in our theorem with Kiritchenko and Timorin. Okay, and finally, in the remaining 5 minutes, I'd like to show you some pictures. The way, come. Structure constants. It's not nothing to do with structure constants, but yeah, here we can. This is just an interpretation. This is some combinatorial language, and as far as I know, this is the first interpretation of this as a sum of certain things over. Well, no. Interpretations. Well, there are many of them, but actually, I don't know that it was whether it was related to polytopes. So, well, this is definition of enhanced patterns, something like this. Well, you can just let me skip it. And this is the first example of my interesting example of a subdivision of Gelfand-Zetlin polytope. Well, there are no unit cubes here, but it is too small. And this pink guy and this gray fellow are inefficient, and the others correspond to monomials. And let me show you, well, not to make this picture too bulky, how to call it. It still is bulky. Mm, how to make it? Okay, so you see that I take a collection of faces. Well, so this is the back face here, and and this trapezoid is basically made up of two faces up there, and you see you take sum of polynomials over all these faces, and you get Lascoux polynomial, and same here. So this is sort of, if beta is equal to -1, as Lascoux taught us, then you can view this as weighted Euler characteristic. Beta is the dimension of your cell. So these are 0-dimensional. These guys' edges are 1-dimensional. You see here beta times this, and beta square is something like that. And in the remaining 30 seconds, yeah, the power of beta is the dimension. Yeah, exactly. So the power of beta is the dimension, and well, when you specialize it, you get just 0-dimensional cells, which are integer points, and you recover our result with the Valencian bloodlet. And well, last slide I wanted to show you is just let me rotate this Gelfand-Zetlin polytope slightly, and
Okay, we have time for a few questions.
yeah. Yeah, yeah. Well, no, but here it is lambda plus the permutation. And as we agreed, permutation, if you permute entries of your partition, you get a composition. So your composition is basically W times lambda, W applied to lambda, or lambda W1, W. That's the relation to composition. Yeah, and so we if you put it like this, we have this interpretation for arbitrary compositions, not just partitions. And answering the question about structure constants, well, this is indeed something really interesting, because we are able to say something about structure constants in in the key polynomial set. Oh well, in like good products of Schubert class. And this can be done thanks to this interpretation. You just intersect. Well, you need to like change your set of faces into sort of equivalent but transversal to another factor, and then you take the intersection of faces. But this helps for like intersected Schubert varieties, like variety. But for Lascoux, well, I would love to know the n goes to infinity. Well, I think it can. Well, in fact, these guys are already stable. Well, you take Grothendieck polynomials, which are K-theoretic analogs of Schubert polynomials, and then you just stabilize them and well, and so what happens if n is going to infinity? Well, it looks like these guys are just well, they how to put it. Lascoux polynomials still form a basis of the ring of polynomials and independent variables. Here, well, I don't know. Maybe you can just embed these Gelfand-Zetlin polytopes one into another and get some sort of int polytope. Well, and actually never thought about that, and I don't know like in which direction to think. Maybe you'll tell me. Yeah, that's right. I see. Yeah. Well, I don't know. That's something I have in mind. Some direction I want to look at, but I don't know yet.
Okay, thank you for your talk.
Thank you, and happy birthday.